Hi students, how are you today? Thank you, me too, I'm doing just fantastic. Okay, we're covering section 11.2. This is going to be on exponential functions, and the purpose and what this is covering is just going to be over in general what is an exponential function, and graphing exponential functions, and solving same base exponential functions. So I know you're wondering, what is an exponential function? Well, an exponential function pretty much has this form. It's going to be f of x equals a to the x, where a is greater than 0, hence it's positive, and also a is not 1. So you might be wondering, why'd you put those restrictions on the value of a? And that number a we're going to call the base of the exponential function. So why does the base have to be greater than 0 and not 1? Well, let's see what happens if it's less than 0. Say if a is negative. Well, if a was negative, why can't a be negative? Say if we had something like negative 2 to the x power. Just if f of x hypothetically was, say, negative 2 to the x power, well, one of the values for x could be 1/2, and if I say negative 2 to the 1/2 power, that's saying the square root of negative 2. And we know that the square root of negative 2 is not real. So we end up having a lot of issues with real numbers if we make that base negative. So good news, base will always be positive. Well, what happens if that base is 1? Well, that's just boring, because 1 to any power is just 1. So it would just be a straight line y equals 1, because 1 to the 0 power is 1, 1 to the first power is 1, 1 to the 1/2 power is square root of 1 is 1, 1 to the 1/3 power is the cube root of 1, which is still 1, 1 to the 9,000 power is just 1 times itself 9,000 times, that's still 1 too. So that's why we take out the, that's why we say a can't be the number 1, because then it's just the line y equals 1. Okay, so let's get into graphing exponential functions. So for example, let's start with what I call the doubling function. And this is f of x equals, 2 to the x. So let's just start off to the side here. I'm going to make a little t-table. Well, actually before I do that, I'm going to call this the x-axis here. And let's call this one right here the y-axis. And we'll say each one of those big, this is 5, that's 10, 5 and 10, negative 5, negative 10. Well, let's start with the t-table. Go here in the corner. Alright, when x is 0, I got 2 to the 0 power. That's here, right? 2 to the 0 power. What's 2 to the 0 power? What's anything to the 0 power? Yeah, we all remember that. Anything to the 0 power is 1. We should remember that. And if we forgot it, we're going to need that for this entire chapter, because that's going to come up a lot. Anything to the 0 power is 1. Even 55,000 to the 0 power is still 1. Well, what if x is 1? What's now we have 2 to the first power, right? What's 2 to the first power? 2. What if x is 2? We have 2 to the second power, 4, right? And what about if x is 3? We have 2 to the third power, which is 8. I'm going to start plotting these points here. There's 0, 1, 1, 2, 2, 4, 3, 8. And I think by the time we get here, what's 2 to the fourth power? 16, right? Look what happened here. You guys notice what happened with my y values as I increased by 1? as I increased x by 1, look what happened. I call this the doubling function because every single time I essentially multiplied those numbers by 2. And that makes sense because every time I increase x by 1, in this case, since this is an exponential function, my values of y will be multiplied by another factor of 2. I'm just erasing this here because let's look on the other side of the x-axis. Let's see what happens when other side of the y-axis. Let's see what happens when x is negative. So what about negative 1? So that would be when x is negative 1, 2 to the negative 1. Well, remember that's now flipped, right? That's 1/2. What about 2 to the negative 2? I'll put my work over here. Well, that's now going to be 1 over 2 to the second power, or 1 over 4. Okay, oops, 1 over 4. Sorry. Yes, I'm fixing it. 1 over 4. When x is negative 3, so I got 2 to the negative third power. This is going to be 1/8. Okay, so let me try to plot these points. When x was 1, I have negative 1, negative 1/4. Alright, I'm going to stop there. Well, let's just pick a big number. Let's just look at x. What would happen if x is negative 10? Then I got 2 to the negative 10. That's 1 over 2 to the 10th power. And I just happen to know that 2 to the 10th power is 1 over... 2 to the 10th power is 1024, so we're looking at 1 over 1024. It's getting a lot smaller and smaller, right? And in fact, what's happening here on this low end is that we got an asymptote. Okay, so this is, I'm going to call this kind of like our parent function of exponential, what we're going to call growth. We're going to call this exponential growth because as x gets bigger, I'm not going to use yellow anymore, as x gets bigger, in this case, y gets bigger. So as x goes to infinity, y goes to infinity. But also, let's see what happens on the other side. As x goes to negative infinity, what does y go to? Yeah, 0, right? Yeah, we call this, what do we call this when it gets closer and closer, but in this case doesn't touch? Yeah, we call this an asymptote. And in theory, this never touches the x-axis. Even when x is negative 1 million... Oops, wait, wrong spot. There it is. In this case, then I'm going to have 2 to the negative 1 millionth power. And that's going to be 1 over 2 to the millionth power. I don't know what that number that is. It's going to be 1 over an extremely big number. It's going to be very, very small, very close to 0, but theoretically it's not 0, is it? No, it's not. So this is the graph of y equals 2 to the x power. And I kind of call this my parent function. One other important piece of this one is that right here, my y-intercept, at least for my parent function, is always at 0, 1. And this even works for any base, like it could have been 3 to the x power. And in that case, guess what? 3 to the 0 power is still 1. Okay. So let's do another exponential function. Let's do f of x equals 1/2 to the x power. Okay. Same thing here. I'll take my asymptotes. Oops. I apologize. I'm going to go back to our last example for just a second. There's one other thing to note here, and that is that my y values down here, do they ever go underneath the x-axis? No, they don't. So my y values are always greater than 0. not even equal to 0. They're always positive. And again, because we said here the asymptote, they can't be 0. And anything, any positive number to a base, whether that base is positive or negative, as we saw here, it's still going to yield a positive value of y, always. And same thing even if we have x to the negative 1/2. But if we're not sure how to graph this, let's look at a table. And real quick, I usually like to call this the halving function, but I'll get to the halving function part in just a minute. Okay, when x is 0, what's 1/2 to the 0 power? Good. Anything to the 0 power is, yeah, even 1/2. Even 0 to the 0 power is 1. Weird, right? Okay, if x is 1, what is y? What is 1/2 to the first power? Good, just 1/2, right? What's 1/2 to the second power? 1/2 squared, 1/4. 1/2 to the third power? Yeah, 1/8. 1/2 to the fourth power? 1/16, right? So what's happening here? It's getting closer and closer now. It's getting smaller and smaller. In fact, kind of looked like what was happening on the right side was the same thing over here that was happening on the left side. I wonder if it's going to be the same in the other direction. So let's try some negative values. I'm going to just make a new t-table up here for negative values. What if x is negative 1? Alright, well, what is 1/2 to the negative 1? To the negative 1 power? Well, that's 1/1/2. Oh man, how are we going to get rid of that? Clear the complex fractions, multiply top and bottom by the denominator. And that's going to be 2/1. Well, that's 2. 1/2 to the negative 1 power is 2. Well, what's 1/2 to the negative 2 power? Hopefully you start seeing these. So this is going to be 1/1/4. Same reasoning now. I have to multiply top and bottom by again that denominator, 4. That's going to give me 4 on the numerator. On the denominator, it's going to be 1/4 times 4. That's just going to be 4. Well, guess what 1/2 to the negative third power is? It ends up being 8. And I'll do one more. To the negative fourth power is 16. And if you didn't get that terribly fast, we're gonna learn these rules here. Oops, that was horrible. Let's try. Still not great, but I think you get the picture. Okay, so for in this case we had 1/2 to the x, and as x gets bigger, what's going on here? Is y going to infinity? Negative infinity, 0. Yeah, it's going to 0, isn't it? And what if x goes to negative infinity? Where's y going? This time positive infinity. It's getting bigger and bigger on the other side. So there's still an asymptote here, but it is here at y equals 0. Just like before. In fact, if we look here, this graph is a flip about the y-axis of this graph. So this graph I call the doubling function. I take every value of y I take every to get from one value of y to the next value of y, at least by one whole unit of x, I have to multiply by 2. So I have to double the value. But in here, to get from one value of y to the next value of y, again, if I'm going up by one unit in x, I'm actually halving the function. a lot of times I think of this function as like if I go halfway to the wall, 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 and keep trying to go halfway to the wall. It's kind of like here. Let me draw that over here. If here I am, and here's the wall. Here's the wall. Okay, I could go halfway to the wall. I'll be here. Another halfway to the wall. I'll be here. Another halfway. I'd be about here, and then here, and then here, and then here, and here, and here. Be getting closer and closer to the wall. In theory, in mathematical theory, at least in Mathmagic land, I wouldn't actually touch the wall. I say in Mathmagic land because in reality, I'm going to hit the wall, right? But mathemagically, no. Okay, so I'm going to formalize a few things here. I'm just going to skip screens. I'm going to get rid of the graph on the back. Bye-bye graph. Okay, so what we call exponential growth. And by exponential growth, we're saying so exponential growth and when we say is exponential growth, that means as x gets bigger, y gets bigger. So as x goes to infinity, y goes to infinity. And this is going to be a to the x if a is strictly greater than 1. So just some examples of exponential growth would be something like what we just saw, 2 to the x power. Or it could be something like f of x is going to be 4.38 to the x power. Or f of x is 1.0001 to the x power. That's gonna grow as well, just really slowly. And what's the domain? Well, this is going to be true of any exponential functions. For all of them, the domain will always be negative infinity to positive infinity. And the range, what were my possible y values? Well, we said that, going back to the graph, we said that y could never be negative. I'll go back to the previous graph here. Said that all the y values can never be negative, and also it can't actually touch 0. It can get insanely close to 0, but that was all the way down here, but it can't actually touch 0. So this is going to be true of all exponential functions, whether they're exponential growth or decay. The range will be 0, not including 0, off to infinity and beyond. Okay, exponential growth's counterpart is what we call exponential decay. And we're going to be seeing lots and lots of good real-life examples of both exponential growth and exponential decay. And the idea of exponential decay is x gets bigger and bigger and bigger, y gets smaller and smaller and smaller until it goes to 0, just not negative. And this happens, again, if the base now is somewhere between 0 and 1. Like we had our 1/2 function. 1/2 is between 0 and 1. In that case, for every 1 unit of x, y went down by a factor of 1/2. So some examples of this might be something like what we just had. 1/2 to the x power. Sometimes we could write this as a decimal. It could be something like 0.99 to the x power. That's like reducing something by 99% every time. Or it could even be something like 0.01 to the x power. It's like finding 1% of a number every time. We'll see more examples like this as the chapter goes along. Okay, we'll do one more graphing example. Throw out our cool chart here, and maybe a little bit more complicated graphing type problem let's try graphing f of x is going to be 3 to the 2x minus 1. Really, Bessling, why'd you do that? Okay, so it's a good idea to probably start out with a t-table here as well. We could start plugging in values until we find happy numbers, but I'm just going to help you out here and tell you which values might be nice to try. So we want this whole number to be, this exponent, to make it easy t-table, that is, we want that number to be like an integer. We don't, what am I trying to say here? Good question. What am I trying to say? I don't know. Let's just see what happens. Let's see what happens, right? If I put 0, I got 3 to the negative 1 power. What's 3 to the negative 1 power? 1 over 1/3. Sorry, excuse me, 1 over 3 to the first, which is 1/3. If x is 1, what do I got? I got 3 to the first power, which is 3. Yeah, see, this works just fine. If I put in x equals 2, what do I got? I got 3 to the third power. That's 27. That's pretty big. That might be off my charts already. Okay, so let's go in the other direction then. Let's see what happens if x is negative 1. Then I'm going to have 3 to the negative 1/3. That's going to be 1 over 27. So if I just plot these points, 0, 1/3, it's pretty small, that's down there, and excuse me, it's hard to be accurate using my stylist. Negative 1 is all the way down here, negative 1/27. When x is 1, we had y is 3, and then when x was 2, we had 27, 5, 10, 15, 20, 27, it's like all the way up there already. So we can see this guy got stretched quite a bit, didn't it? It's going to go really steep, it's going to grow really fast. And it's going to grow off to infinity on this side, and it's going to go down to negative infinity on that side. How did I know that? How did I know this was going to go to negative infinity? Well, it helps to even evaluate the function ahead of time and ask yourself, is this growth or decay? This is growth, because this number, this base of the exponent 3, is bigger than 1. Okay. And if it was between 0 and 1, it would have hypothetically, I'm just drawing this out here, it would have had this general shape where it would have gone off to infinity on that side and gone to 0 on that side. But it wasn't, so I'm erasing that now. Me. Okay. Second part of this lesson is going to be solving similar bases. So let's just do an easy one. 2 to the x power equals 2 to the second power. What does x equal? Well, don't say it out loud. Hey, take that back. Don't say that. Okay, so I'm going, hey, 2 to what power equals 2 to the second power? Well, it has to be the second power, right? Okay, what if I were to do this in another way? 2 to the x power equals 4. So what I recognize is that, hey, 4 is a nice power of 2. I could kind of rewrite 4 as like 2 to the 2 squared. And now I could just go x equals 2. Here's the idea. We need the same base. If we have the same base, like we kind of started with in this form, then we can immediately just solve the exponents. So some number to this, some number to x power equals that same number to some other power. We'll just set the two sides equal to each other. And this is going to be the strategy that we will need to solve more complicated problems. Okay, so let's try more complicated problems. Sound like a good idea? Sounds like a horrible idea? Too bad, we're doing it. Okay, so what if I had something like, what if it was something like 9 to the x power equals 27? Okay, so we want to look at this now. Now this is a little bit more complicated. But we kind of look at these two numbers, 9 and 27, and go, okay, can I write them as the same base? Well, okay, yeah, 9 times 3 is 27, but isn't 3 squared 9, and isn't 3 cubed 27? Yeah, so check it. Here's what I'm going to do. I'm going to, since I realize that there's a common base between these two numbers, I'm going to rewrite them in terms of bases of 3. That is, 9 squared is 3 squared. Sorry, 9 is 3 squared and 27 is 3 cubed. Now, let's see what I did here on the right. I'm going 3 squared to the x power. Since I'm exponentiating these, I multiply these. So I can now rewrite this as 3 to the 2x equals 3 cubed. Now I have the same base. Now I could just set the exponents equal to each other. 2x equals 3, divide by 2. X is 3 halves. Smashing good time, is it not? Okay, let's try one more problem. I'll make it a hard one. And this will be it. Make it a nice and hard one. Okay, I'm going to make this one up right now. Okay, let's say I had something like 8 to the 2x equals 4 to the 3x minus 1. Oh man, what am I doing here? Too bad. Okay, so step number 1 is I look at those two numbers and I try to see, is there a common base I could use between the two? And be careful, I don't want to use 4. What's the best base I could use in this case? Good, 2. Alright, now my next step is I'm simply going to rewrite 8 as a power of 2. So 8 to what power equals, sorry, 2 to what power equals 8? 2 cubed. Now when I'm doing this, sorry, my stylus is getting weird on me. Again, look what I did. I just rewrote 8. I left the 2x alone first step. Can I do the same thing with 4? Yeah, I'm going to rewrite this as 2 squared to the 3x minus 1. So on the right side now, again, now I'm multiplying these exponents. So this is going to be 2x to the 6x. And I need to multiply on the right side too, but I have to be a little careful that I distribute in the 2 into the both 3x and the negative 1. So let's keep going here. So this is going to be 2 to the 6x. Uh-oh. I think this is going to be undefined, but too bad. So I got 2 to the 6x on the left side and 2 to the 6x minus 2 on the right side. So the last thing I need to do is just set these two equal to each other. And did you hear me say, uh-oh, I think this is going to be undefined? Because I'm saying, hey, some number, 6 times some number equals 6 times some number minus 2. Well, it's not going to take me long to realize if I subtract 6x to both sides, I'm going to have a 0 and a negative 2. So this problem, my bad, happened to be undefined. And that's just sometimes what happens when I make up problems. But the steps were all there, the logic was all there. So hopefully you can understand that, do the homework, and you can go back to this video anytime, and it will be on the Chapter 11 playlist. Thank you.